Okay, so we have one more presentation for the Rack and Power section. So again, we've got a couple of minutes just before that time, just to make sure we're on time with the schedule. But if you give us a couple of minutes, we'll continue shortly.
Me with the laptop, yes. No, just setting it up. Is that okay? Oh. I just want to see if Jamie, this still works. Okay. Oh, there is a HDMI cable that would help. This is here. That should just go. Come on. Oh, there we are. And oh, it moves. All yours. And this is a pointer.
We have 5 minutes.
Oh, we have 5 minutes. Do you need to dance or what?
Timer. Timer says you are not allowed.
You're not allowed. So all these guys have to wait for beers, right? And we are standing in between that, right? So we better hurry up.
We try to make it as comfortable. Shall we start?
It's not broken.
There are no seconds on the screen. I think we can start, right? Yeah. Okay. So, hi, welcome to the latest and greatest meeting for today. So, today we are talking about the efficiency improvements and about the power of the ORv3 and the actual status. So, I'm Cihan Aydin, and this is my colleague Harry. This way. Okay, short content which you can read. So we will go over the slides and then talk in detail. So short refresh on the specs. So we have the PSU called Rectifier here in this presentation. It's a 3 kV design with 51 volts fixed voltage for zero load and going down to 50.5 for full load, which is 500 millivolts of a droop. And the hold-up time is 20 milliseconds, and the peak efficiency is 97.5, and at full load we have 96.5. So we have also current share in place, active current share bus, which is routed through the shelf, and as well we have a droop voltage on top where the PSUs adjust the output voltage. So the communication, we have I2C and Modbus. Default is Modbus for Meta PSUs. And the size, I think everybody knows, it's 7340 to 520. On the other hand, we have the shelf. So we have 6 PSUs in one shelf, and it's N+1 redundancy. So you have 15 kV with redundancy and 18 kV without. The output voltage is same like for the PSU. Also, we can mention the 48 volt, it's for the BBU. So the PSU is supporting the BBU, and once there is an overcurrent or overload or any other event, so the PSU is decreasing the voltage to 48 so that the BBU kicks in and takes over the load. The load for the shelf is 300 amps, and we have the bar clip in place here. So yeah, you will notice I make my life easy. I'm a design engineer, so I just take my testing data and talk about it. So here, I'm happy to say we are already in mass production with the unit now. And to verify it, we just picked 3 units out of the mass production and did some measurements here. And you can see that we achieve the efficiency goals and yeah. Next point is, which I wanted to highlight for this PSU, is the pulse power requirement. So for GPU loads, especially for AI applications. So you can have PSU load steps up to 150%. And in this case, we did it on the PSU level, jumping from 10 to 150% without entering the 48 volt. So it's normal use case. Next step is also for the shelf. I mean, you have also the pulse power requirement here. So you have a start point and end point and defined timings which you need to fulfill. And you can see also on the shelf level, so it's no problem to share the load and just do the 10 to 150% load step. Next slide shows the shelf to BBU load. And so here we are doing a load step together from our PSUs or the shelf together with the BBU shelf. And we're jumping to 150% for 10 seconds or longer. And just to show that there's a smooth transition, and you see that here's the load step. And you see that the PSU decreases the voltage and the BBU kicks in and they share the load, and there's no interruption in the output voltage. So we have as well a common shelf, so it's called common shelf, and the difference to the standard shelf is a PMC. So for the standard shelf, we have a PMI. So it's no controller or anything else on it. It's just the signals routed out. You can connect shelves daisy chain so that they can communicate and know the shelf, the share voltage. And the difference here is you don't have the share bus routed through both, but so nevertheless, we are passing the requirements and fulfilling and the spec. Here's a short overview about our actual portfolio. So you have the 1OU shelf, which is the standard shelf, which I've shown. The PSU is 3 kV model. We have as well PMC. This is the one you can use with embedded Linux in it. And as well, we have a 2OU shelf, 5 kV PSU, and a dummy load, which is manufactured for Meta for testing reasons.
Thank you, Cihan. So just carrying on with it, so I will provide the details on the work we've been doing at AE on all the important attributes of the power shelf. So moving on, here is the latest efficiency data. Just like Cihan pointed out, we are meeting. In fact, I would say this is, a while back, getting close to 98% efficiency wasn't heard of. We are approaching numbers like 97.83, close to 98%. I mean, the next step is almost impossible. I wouldn't say impossible, but it's hard to get incremental effects. But and the challenging aspect is, this PSU goes down all the way to 230 volts and meeting efficiency target there as well. So all across 230 and all the way up to 277. Moving on, just an update on the ITHD and power factor. Those are important attributes as well. So essentially, if you remember the previous presentation, there was a lot of work in progress. We were at lower loads. It's very, very difficult to meet those targets. So these are the mass production units where we are not only meeting or exceeding the meta spec and the details of the spec. These are the new things I just wanted to bring out to everyone's attention. This is an important part when you have the AC interruptions, and AC interruptions happen under various conditions. And what it does is it causes a lot of inrush current at the front end of the power supply. So here are the real results where you will see that this is tested at half load, 277. There's a 20 millisecond interruption, and this is at 277 at full load. And you will see there is absolutely no impact on, the pictures may be a little blurry, but if you look at it, there is no impact. And this is really important from sizing of the breakers on the front end, that that they don't see higher inrush current. And we do this by having a well-controlled inrush current limiting circuit. This is, again, you not only do that at loads, but it's also important to perform this test at the various angles of the AC turn-off at different angles. So this, AC line inrush current is still controlled and sinusoidal at different AC, the angles when you shut off the power supply. So that shows you that there is absolutely no impact on the power supply, and the inrush current is very smooth. Moving on. Cihan mentioned earlier that the transition happens, the BBU goes from 51 to 48 volts, and that's when the BBU kicks in. And what I want to point out is when that happens, the PSU has to stay there for 6 milliseconds and to ensure, and then the BBU will come into picture. And this happens 2 cases. The AC line has disappeared, or then there are transients in the system. And those transients could be the power goes up to 3.3 kilowatts or up to 3.6 kilowatts. And Delta showed those use cases earlier, right? And you saw those. And there is also a profile, which is a repetitive peak pulse. So we have to ensure that we meet the performance under those conditions, and there is, the PSU behaves normally. So to that effect, here's an example. In the previous presentation, I covered a lot of use cases, but here I'm just showing you the highlight here when there is 150% load on the system. And what happens there is, as you can see, the voltage drops from 51 to 48 here, and this is where the ice shear kicks in because the load is higher. You need to provide more load, and at the end, either if the AC returns, the unit can come back. Otherwise, the power supply will gracefully shut off. And what's important is these are the details. The time is provided by the bulk capacitor to help maintain that voltage, and there is a very smooth transition when that happens. Moving on, another key aspect, or in fact very challenging aspect, is the PLD transitions in a PSU, right? So, in this case, we are talking about when there is an AC line interruption for 25 milliseconds. This is just one use case, and there are 6 PSUs in the system, right? And what's important is if AC shuts down due to AC load and there is no provision, there was a subtlety in the previous spec which is, the power will take up to 4 seconds for power to return. But the output fault recovery is 5 seconds. So what that was doing is your power supply was shutting down. So all we are saying is that these are the learnings as we went through the whole development for a year and a half. Then we had to update the spec on T-on no BBU for 1 second. So essentially what that did is some like 1 second to wait for the max random timer. We adjusted that to 3 seconds. And so to make the long story short, when you say previously when this thing was not implemented, you see the PSU, there's no fix and the PSU will shut down. Having the fix, what it does is you see there is absolutely no, once we did this 3-second adjustment, you will see there is no change and the PSU and the shelf behaves absolutely normally. Moving on, just want to showcase the products we have. Just like Delta, we have a 1OU power shelf. This shows you, in fact, the connectors on the back. We have the power supplies, 3 kilowatt, 5 kilowatt in works, just like everybody else. And essentially, that paves the path for immersion as the power goes from, in a shelf, 50 kilowatts to 100 kilowatts and beyond. We have power management controllers, PMI as well, it depends on the application. And we have the EIA 19-inch 2RU power shelf for the applications, because as you've probably seen, there are a lot of 19-inch racks out there, 21. So essentially, we're trying to address both of those markets with the solution. So I guess that brings us almost to the end of the presentation. So, so all the details are here. Here are the details for the products, the project wiki, mailing list. We have been discussing this at Rack and Power. There were a lot of presentations at Rack and Power as we move towards higher power. And all I can say is I look forward to seeing you in Rack and Power so we can talk about power needs and how we shape the power for the future. So I think that brings to the end of presentation. Any questions? If not, thank you. All right, we gave you a few minutes back.
Go for the beer.
Exactly. Thank you.
Thank you, everyone. That's it for today.